Let's start the class by sharing the presentation. Okay, now the board is visible.
Yes,
Yes,
sir.
yes,
Yes, sir.
Okay, so let me recap the things that we discussed before the earlier classes. So we were discussing in the last class, we have started the power diode, which is a little different from the signal diode as I discussed. It is made for very high current, and as it has to carry very high current, the problem is there because to give this feature of carrying very high current, we have to increase the doping level of both P and N substrate in the PN junction. So that will result in a very small PIV. Uh, to to overcome that problem, to overcome the problem of less PIV, what we do, we change the configuration and we incorporate another layer in between the P plus and N plus layer, that is the N minus layer. Okay, so the plus denotes the uh, elevation in the doping level. Normally the doping level is in the order of 10 to the power 16 per cm per cubic centimeter. Now the plus layer, that means the when we are writing P plus, so that means the carrier density in that particular substrate, it is around 10 to the power 19 per centimeter cube, and minus denotes the less concentration or less impurity in the order of 10 to the power 14 per centimeter cube. So that is the difference. Normally we take it 10 to the power 16. Now plus means 10 to the power 19 and minus means 10 to the power 14. So that is the difference. So in this modified configuration, which is practically used for the power diodes which is available in the market, generally these three layers are available. The P plus having the concentration of area density of 10 to the power 19 per centimeter cube, and N minus having the 10 to the power 14. So I have written that here. So, and having different length, that depends on the applications. So I have discussed there are different types of power diode depending on the application. The length of the particular layers will vary. So there are different types of diodes as I discussed: general purpose diode, high speed diode, so fast recovery diode, because for making it high speed you have to reduce the recovery time, reverse recovery time. So that I will discuss today, what is the reverse recovery phenomena and what is the time required for that. The super fast recovery diode and ultra fast recovery diode are the two variations of this high speed recovery diode. And then another thing is that is the Schottky diode, which is not a PN junction diode. So that also I will discuss today. So these are the thing we discussed in the last class. So let me start today's topic. Okay, just a minute. I have to create a new board. Okay. Now, what is the necessity of having the N minus layer? To understand that, you have to understand the basic phenomena, basic principles of normal p-n junction. Now, in the normal p-n junction, you know that we have a p layer. Just a minute. You have a p layer and an n layer. So this is the p layer and this is the n layer. And the p has a more carrier density. What type of carriers are excess carriers are there in p type?
Whole
Holes.
holes.
Holes. And in n times electrons.
Electron.
Okay. Now there are two phenomena occurs in diode or say semiconductor type material. These two phenomena is called the drift and the diffusion. So you know the difference. What is the drift and diffusion? Okay, so drift is generally created by the electric field.
Forward
Okay,
bias.
so the velocity that created by the electric field in the carriers is called the drift. And diffusion is generally occurred due to the variation in concentration of the carriers. Okay, if there is a change in spatial density in the carriers, then the diffusion occurs. Okay, and you know that though uh, there are a few terms which is called uh, first one is the majority carrier. Majority carrier and minority carrier. Have you heard these terms?
Yes.
Yes, sir.
What are these? What is the majority carrier for this p type substrate, and what is the majority carrier for n type substrate? So here the majority carrier is
P
whole,
type.
isn't it?
Holes.
Here the majority carrier is carriers are whole, and here electrons. Okay, so these are the majority carriers, but there will be some electron as well due to some for normal condition due to some thermally generated phenomena. There will be some carrier electrons in the p-type substrate also, and that will be considered as a minority carrier in p-type substrate. And here we have holes for n-type substrate, which will be considered as a minority. Okay, and remember that p-n junction diodes are basically minority carrier device. Okay, now when we keep like this, what happens due to this diffusion? The electrons from the this n substrate and the holes from these p substrates diffused along this junction and creates what is called a depletion layer. Okay, so this creates a depletion layer near this junction. Okay, so due to this diffusion, isn't it? So that means the electron, which is the majority carrier in n side, diffused in this side, and holes diffused in this side. Okay, so thereby there is a depletion layer, or it is called the space charge region, because here you have, before that it was a neutral. Now due to this depletion, here the positive potential is created, and here the negative potentials are created. So this is called the depletion layer, or space charge region. Okay, have you understood why it happens? When the electrons
Yes, sir.
will move to the p side, then there will be some ionized carrier. Okay, so therefore this type of depletion layer occurs, and what happens due to that is a change in the voltage or potential. So that means if you take this is as a junction, then the potential changes will be like this. Okay, so let me draw like this. Okay, now so due to this you have a potential barrier. This is called the potential barrier. Okay, now so this is when it is open circuited, when the PN junction is open circuited. This is the picture, and there is a change in the uh, change in the charge, change in the voltage as well near about this depletion layer. So that is the normal phenomena. Now, when there are two phenomena can be occurred after that, one is called the reverse bias and another is called the forward bias. Okay, so what do you mean by that? Actually, though we call that forward bias and reverse bias is basically done externally, but this is the internal phenomena of the device. It is not an external thing. It's the internal phenomena of the device. Okay, so that means the forward bias is not only when we are connecting the p side to the positive and n side to the negative. The forward bias means the change in a carrier concentration along the depletion layer. Okay, so that you should remember, because the forward bias and reverse bias is a complete device phenomena, not the external phenomena. Okay, so let me discuss that when the forward bias is occurred. Now, when an external voltage is applied, so that means the same PN junction, if I draw it again here you have the P and here you have the N. And if we connect this to some positive and this to some negative, sorry, negative, then what happens? The the voltage, the potential barrier which was created due to the open circuit or due to the diffusion of the carriers, that potential barrier will be reduced by this voltage. Okay, so that potential will be opposed by the external voltage applied. Height of the potential barrier, height of this potential barrier, this is the height when it is open circuited, that potential barrier height will be reduced to some extent due to this forward biased. Okay, so when it is forward biased, this will be reduced, and how much it will be reduced, that depends on the amount of the that magnitude or the amplitude of the voltage you have applied. Okay, so that is the when it is forward biased. Okay, and what happens here if the initially it was having this length, if initially this was the length of the width, sorry, not the length, the width, if the width was initially the deflection layer width was W0, after the forward biased, the width will be reduced to some different width W. Okay, so that is the change in the space charge region, or you can say depletion layer. So that will be reduced. Is that clear? Now, if we do the opposite thing, that means if we apply the negative to the P substrate and positive the N substrate, what happens? The width of the depletion layer will be increased. Okay, it will be increased to this. If initially it was W0, it will be W after that. That is the change in the width of the depletion layer or space charge region. Okay, so that is the change, and also there will be a change in the height of the potential barrier, because as you can see that width has increased, so therefore the voltage difference or potential difference between these two thing will increase, and it will increase the potential barrier height. So that is due to the reverse bias. Okay, so that is meant by the forward bias and reverse bias. And not only that, during this forward bias and also in the reverse bias, we have to discuss how the current flows. Okay, now you will ask me that in the reverse bias, how the current will flow, isn't it? So is it possible in the reverse bias any current can flow? Is it possible?
Due to magnetic area, some current may be flow.
Why?
The circulation current due to magnetic area.
Eh?
Due to magnetic area, some current may be flow. Due to magnetic area, some current may be flow, but it is very small.
Uh, can you explain more clearly?
So, because magnetic area is the opposite thing of the magnetic area. So where
Hmm.
P type, there are magnetic area is electron. So if we keep forward bias, this will behave as a if we give reverse bias voltage, but the magnetic area will behave as a forward bias thing.
Okay. Actually, there are
The
some
small current.
thermally generated carrier. Okay, so that doesn't depends on the voltage applied. Some thermally generated carriers are there, which is called the minority carrier. That doesn't depends on uh, the the voltage applied. Now, generally, what happens? Uh, the there is a small gradients in minority carrier densities due to this. Okay, so let me draw something, then I can explain it in a better way. So what happens here in case of reverse bias? Not only reverse bias, always the minority this current can flow. Now this is the level. Okay, so that depends again on the substrate. It may not be equal for P and N substrate. Okay, so this is the level of this minority carrier NP0, because N in case of P, N is the electron is the minority carrier, isn't it? So suppose this is the NP0, which is the level of the minority carrier or the density of the minority carrier, and here it is Pn0. Okay, so that is the level of the minority carrier in the N side. That means the concentration of the hole in N due to the thermally generated carrier. So that concentration or density doesn't remain constant with respect to the length. So it changes like this. So let me draw with this. This concentration changes like this. This is the length. So I have to draw within this. Within this. Okay, because this is the length. So this is how it changes. It changes exponentially. Okay, so we can say this is the change or gradient in the uh, minority carrier in P and N substrates. So due to this gradient, if this gradient is low, if this gradient is very small, so due to this gradient, there will be some diffusing minority carriers towards the depletion layer. Okay, so this gradient, which gradient? This gradient. So this gradient will create some diffusion across the depletion layer. Okay. Now, when this diffusion carrier reach the depletion layer, are you getting? When this diffusing carrier means here it is N, that is when electron diffuses in this and hole diffuses in this. Now what happens? Can you tell me what happens? Now what happens? There is already a potential large electric field present due to this space charge region. Okay, so when this minority carrier or diffusing minority carriers reach the depletion layers, the large electric fields which is present in the space charge layer, which will sweep the carriers to the electronic this neutral region. That means that P will go this side and electron will go this side. Okay, so due to this, so already there is a field here due to this. Already field is there present. Now whatever the whole will come here due to this diffusion, that will be swept by this whatever this field present in there due to the space charge region. An electron will swept to this N side and the holes will be swept to the P side, and that will constitute the current, which is termed as a leakage current, or sometimes it is also called the reverse saturation current. Are you getting? If you have any problem in understanding, you can point it now. Today the attendance is not that good. Why? Only 35 students are present. So anyway, so have you understood this point? How the reverse or the leakage current flows?
Yes. Yes.
So any doubt? Okay. Now the thing is how the forward bias during the forward bias how the current flows. Now, as I told you that during the forward bias, the potential barrier, the height of the potential barrier reduces. Okay, so before that there is an equilibrium, but when the height of this barrier is reduced, the equilibrium is destroyed. Now you'll ask me what type of equilibrium you are telling about, you are saying about. Actually, that I have not discussed. There is an equilibrium between uh, this drift and diffusion. So I don't have that much time to go in that details. Okay, so during this open circuit, there is some equilibrium is established between this drift and diffusion. So whenever the device become forward biased and whenever the potential barrier is reduced, so there is a there is a destruction of this equilibrium, and as a result, there is an enormous increase in minority carrier densities along the along the space charge region that I will show you how the density is changed. Okay, so if I take the earlier one, that is this one. So this is your figure 1 and this is your figure 2. So if I refer the figure 1, because that is the figure corresponding to forward bias. So if I refer the figure 1, what happens? So along this space charge region, there is a increase in minority carriers. Okay, so I should draw it by the blue. That will be better. Okay, so let me draw like this. So okay, so this is the again this level again dictated by this Pn0, and this level is Np0. So it cannot go beyond that. So that is the minimum level of this minority carrier. Okay, so that is the change in minority carrier distribution in the forward bias situation. So this is the change in minority. This distribution are exponential, though from the figure it is not possible to understand that it is exponential, but you have to note it down that the distributions are completely exponential. Okay, now due to this change in this distribution uh, along this space charge region, it is also called the carrier injection, because previously as you can see that previously that the distribution was not like this. So this is the accumulation of the minority carrier along these regions is called the is also called the carrier injection, that is defined as the excess carrier density. Okay, above the thermal equilibrium value. So these are the thermal equilibrium value. Okay, so above this thermal equilibrium value, there is an excess uh, excess carrier density. So that is also termed as a carrier injection. Okay. Now, due to this, again, this gradient, what happens? Huge diffusion current flows across this depletion layers, and that constitutes the main component of the diode current, and very small component due to the drift current. So mainly it is the diffusion current which we get as a diode current. Okay, so this is all about the normal PN junction. So we have three different condition. One is open circuited condition where we have uh, on হ্যাঁ 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 না 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 না, আমি আমার পার্টটাই নিচ্ছি মানে যেটা নিয়েছিলাম গতবার। তোমার কি এই সেকশনে আমি ওদেরই ক্লাস নিচ্ছি এখন। হ্যাঁ হ্যাঁ ক্লাস নিচ্ছি। না ঠিক আছে কোনো অসুবিধা নেই, তুমি ওদের কি ক্লাস নেবে? তোমার কি এ সেকশন পড়েছে তো? আচ্ছা, হ্যাঁ হ্যাঁ সে তো পেয়ে যাবে, সে আমি তোমাকে না হলে পাঠিয়ে দেবো। ঠিক আছে। Sorry. So that means I was discussing the normal the PN junction. Here we have seen the three states when one state it is open circuited, another it was forward bias, and in the third one it was reverse bias. Now the main thing is in all these states there is a layer which is called the depletion layer and also called the space charge region, and that has a very important role in the diode characteristics. Okay, now due to the space charge region, potential barriers is created around the junction, and in the forward bias, this height of this potential barrier is reduced, and in the reverse bias, the height of the potential barrier is increased. And in reverse bias, there is only current that is due to the reverse saturation current or the leakage current or the minority carrier current. In forward bias also the current is mainly formed due to this minority carriers currents are there due to the minority carriers only, and diffusion current. So if you have any question you can ask me, so then I will discuss the thing related to the power diode. Now let us go for the power diode. Now, instead of two layers in power diode, you know that there are three layers. Okay, so if I draw similar way as I have drawn so there will be three layers. So what is the first layer? Can anybody tell me what is the first layer in power
P
diode?
plus,
So it is a P
P
plus,
plus, N minus, and N plus.
N minus, and N plus. Okay, so these are the three layers present in the power diode. So let me first discuss the open circuited condition. Now this N minus layer is here termed as the drift region. This n minus layer here is termed as a drift region. Drift region. Okay, so this is the main difference. Here's the main difference between the signal diode, normal diode, and power diode. Okay, and this dictates or determines the what is called the PIV, that reverse breakdown voltage, and also the on-state resistance or on-state voltage drop. So these two things are determined by the drift region itself. Okay, the primary objective of providing this N minus or drift region is that it absorbs the depletion layer. So that depletion layer I have discussed in case of this this PN junction. Actually, here this N minus layer is provided to absorb the depletion layer. Okay, so there is a junction called P plus N minus junction. That means this this creates a depletion layer. It is completely absorbed by this N minus layer. So that is the main objective of providing this N minus layer in between P plus and N minus substrate. Okay. Now, as I told you that we get two advantage out of this. The first one is the reverse breakdown voltage increases.
পাওয়ার ডায়োডের বেসিসটা একবার বলবেন?
বলছি দাঁড়া।
পাওয়ার ডায়োডের বেসিসটা যেটা বলছেন একবার বলবেন? আমার কানেকশন চলে গেছিল।
Just a minute. And number two, what I told you that it gives a open gives more linear characteristics. We should write. I will discuss this. Okay, so these are the two objects. এবার বলো কি বলছিলে? শুনতে পেলাম না তোমার কথাটা।
স্যার ওই পাওয়ার ডায়োডের স্টার্টিং এ যেটা বলছিলেন না, এটা একবার বলবেন? ওখানে আমার কানেকশন চলে গেছিল।
পাওয়ার ডায়োডের স্টার্টিং এ কি বললাম? না, পাওয়ার ডায়োডের in power diode the main difference between the power diode and signal diode is this region which is having N minus substrate, which is also called drift region. Okay, and the primary objective of providing this N minus drift region is that it absorbs the the depletion layer or space charge region created between the P plus and N minus substrate. Okay, so that is the main objective. Uh, and it results in two things, two advantages. The first one is the reverse breakdown voltage increases, because if we don't have that, but still if we have elevated concentration, then the PIV, that reverse breakdown voltage, will be reduced. So it slightly increases the reverse breakdown voltage, and it also determines the width of the drift region, determines the reverse breakdown voltage. So that is one advantage we get. Another advantage is it is also disadvantage, you can say, that it increases the on-state voltage drop because it increases the resistance. Okay, but if as it increases the resistance or on-state voltage drop, it the characteristics That characteristics becomes almost linear, okay, instead of exponential. So generally what we get in case of, if we can remember, in case of signal diode, the characteristics we get almost exponential, isn't it? This type of characteristics we get. This is the reverse saturation, and this is the reverse breakdown voltage. This is the reverse breakdown voltage. Okay, and you don't have the, this is for the normal, this for the normal diode. Now for power diode, what we get? We get almost linear characteristics. So let me draw like this. So this characteristic is almost linear. It is very difficult to draw this type of board. Okay, so that is the advantage of the power diode. Okay, so that means two advantage we are getting having this n minus layer. First one is reverse breakdown voltage increases, and the second one is it gives more linear characteristics. Okay. Now I will go for the other two things that I told you that I will discuss today. The first one is the reverse recovery phenomena. Reverse recovery phenomena. Now, what happens in the last class also I told you that suppose let us draw a simple diode. A power diode is there. In series, you have an inductance. So the inductance may be there or may not be there. If it is not there also, there may be some stray inductance. So this inductance can be some physical inductance or can be an effective inductance, effective stray inductance. Okay, so this was the normal case when the diode was forward bias and it was carrying the forward bias current, and that is the load. Okay, this is the supply voltage. Now, what happens if we want to switch off the diode? We apply some negative voltage. Okay, so that means when we want to switch off this, we apply some negative voltage, and it takes some time to get switched off completely, and that time is called the off time. But this off time has two components. One is called the fall time and another is called the reverse recovery time, as I discussed in the last class. So that means whenever we apply some voltage, if we count the time from that instant, apply some reverse voltage to make the device switch off. If I start counting the time from that instant, the total time it will take to switch off completely is called the off time. Now this off time will have two components. One is called the fall time and another is called the reverse recovery time. Okay, so if I draw the phenomena by a figure, a diagram, if the current is like this, if suppose there is a forward current like this, and at this instant I have applied the reverse bias. Now what happens? The current will fall. The current will fall. Current will fall like this, then it will go like this. আমার তো আমি একটা ক্লাসে আছি, আমি তোমাকে একটু পরে কল ব্যাক করছি, জাস্ট 15 মিনিট পর, হ্যাঁ? Okay, so as I told you that this total time starting from this instant to get completely switch off, this total time is termed as T off. Okay, so this time as it's called T off time. Now this time, okay, when it becomes the crosses the zero is called the T fall time, and rest of the time in off time is termed as reverse recovery time, TRR, which has again two components, T1 and T2. Okay, so this instant when the here the reverse voltage is applied. Here the reverse voltage is applied. Why? To switch off the diode. Then this phenomena is occurred. This is called the reverse recovery phenomenon. You have understood? Okay.
Yes, sir.
Now, so I would discuss like this. Suppose there is an inductor. Okay. Now, whenever there is a forward current is flowing like this. What will be the voltage drop? If the current is steady current, is a DC current, there will be no voltage drop. But if the current is an alternating, or if there is any change in current, then there will be a voltage drop which will be in the opposing direction, and that voltage drop is defined by LDIDT. That you know, I think everybody. So everybody understand this point, isn't it? Okay.
Yes, sir.
Yes.
Now here we have three different situation. The first situation where I have a forward current. I have a forward current I. Okay, but the thing is the current is reducing. Okay, so that means what I can write, that DIDT is less than 0. The current gradient is negative. That means the current is reducing. Can you tell me for which state I am talking about? Bolo?
Fall time. Fall.
This is only for fall time. Only for fall time. Not for the others. So you can write there is a current I and change in current. So due to this change in current, there will be some voltage developed. Can you tell me in which direction the voltage will be developed? The voltage will be developed in this way. Then this inductor will act as a source. This thing you should understand very clearly, because this concept will be used throughout the power electronics class. Now the second point, I have the same inductor, but the current in the reverse direction. Okay, so that means this is a negative current, and didt. What is the value of didt? Again, that is also negative. You see, for which state I am talking about this?
T1.
This is for T1. So again, I will get this type of voltage induced. The third one, so I can write this is for T1 duration. T1, and third one for your T2. Now I have the inductance. What is the direction of the current in the T2?
Negative.
Negative only, isn't it? Now what is the second thing, didt?
Positive.
Positive. What will be the direction voltage induced? Okay. Is that clear? Okay. Now in all this condition, I have already applied the negative voltage. Already I have applied the negative voltage, isn't it? That is for making the device switch off. So this is the Vs already you have applied. So that means here we can write minus Vs plus, what we can write? Minus Vs plus didt. Here it is minus Vs plus didt. But here it is minus Vs minus didt, because you see is proper polarity, these two voltages are added. So proper series addition. You see this minus plus minus plus. Are you getting this point?
Yes. Yes, sir.
Or we can write minus Vs plus LDIdt. So here these two voltages are added. So that will create the problem. So that means in the T2 state, the voltage, source voltage, and the voltage in the induced across the inductor will be added to each other, and if that exceeds the reverse breakdown voltage or peak inverse voltage of the device, then it will damage the device or diode in this case, unless protected. Is that clear? Are you getting? I can
Sir,
write
one
also
of the
for you.
pointer.
I will write this. If this, because you see this voltage is basically reverse voltage minus. Okay. So if this, or I can write the amplitude only. If this amplitude this voltage, this reverse voltage. Is so high that it exceeds the PIV of the device or the diode, in this case, diode, it damages okay. Have you understood?
Yes, sir.
Now, can you tell me how can I minimize this? But who is responsible for this voltage? Now, again, VS will be there, but only the thing you can minimize is LDIDT, isn't it? The first one is inductance, you can minimize, but that is not in your hand because if you need inductance, you have to apply that. And if some stray inductance are coming, that you can consider for reducing. Okay, so the VL value you can anyway you can change, but not in that amount. What else you can change? What else you can modify to get a reduced LDIDT? The main thing is the slope. Now, who is dictating this slope? This slope depends on the device itself. Isn't it? So this DIDT slope, which is coming at the end stage of this device recovery, is completely depends on the device itself. I can explain, but again I have to go in the this device level. Okay, I will discuss in the next class why we are getting exactly this slope. Now, if we can if we can reduce this slope, how we can reduce this slope? Can you suggest how we can reduce this slope? Make it steep or make it flat?
Latter.
What is the
Flat.
in what way we have to change? Like this, making this, or making flatter?
The second one.
Which one? This
Latter.
one or two? Which we should go for?
Flat.
Huh?
Flatter.
Two, sir. Two, sir. Latter.
Two,
Flatter.
two. So that means if we have the device having the two nature, then we can get less LDIDT, and that is called the soft recovery diode. So two is called the soft recovery diode. Okay, or in brief you can write SRD, soft recovery diode. And the first one is called the hard recovery diode. hard recovery diode or HRD. Okay, so these two are the variation which depends on the reverse recovery time. So that means we can write that this DIDT uh, at or during which time T2 time of TRR. This DIDT of this SRD is less than DIDT of HRD. Is it clear? Is the thing clear? Why what is the soft recovery diode and hard recovery diode? This depends on the design.
Yes.
Once the diode is made, once the diode is manufactured, then you cannot change this time. So this depends on the design of the diode, design of the substrate. Okay, but once the diode is made, when you have already purchased the diode and you have to you have to protect your diode. How you can do that? That I will discuss. Okay, so generally what is done to protect the diode, we use a circuit which is called the snubber circuit. So this is the L and D. With that in parallel, we have to connect this branch. Series combination of resistance and inductance, capacitance. And I will explain how it will protect the device in reverse recovery situation. Okay. Now what happens? Why it takes the reverse recovery time? That is when the current flows in the negative direction. Okay, then there is some charge is formed. To discharge that charge, it takes the T2 time. I will discuss it in details in the next class. To discharge that, so suppose there can be you can think of some capacitance which is there across the PN junction. To this and during this negative current, this capacitance is charged in the negative direction, and to discharge this capacitance, we need some time, and that time is T2. Okay. Now, if we have this capacitance, another capacitance is parallel, and which is much less time constant compared to the capacitance of the diode, then any kind of this DIDT or any kind of this uh, change in the voltage will be bypassed through the capacitor. Okay, so that means the voltage, if the voltage is created due to this LDIDT, so that will be bypassed through the capacitor. And you will ask me then why the resistance is used. Now, the resistance is used to detune the possibility of LC oscillation. Detune means suppose in this circuits you have some L already, And if you are using C, there is a possibility of LC oscillation. LC oscillation. Okay. And why the oscillation occurs? I think you know that if there is some resonance, okay, so then the LC oscillation can occur in the circuit. To avoid that, we use a resistance which will detune the the LC combination oscillation. Okay, so that is the purpose of using this resistance. But the capacitance is used to bypass the high voltage which is created by this LDIDT. Okay, so this is called the Snubber circuit, but this Snubber circuit has another objective that I will discuss later. But this is the first objective, which is to bypass the LDIDT voltage which is created in the reverse recovery. So if you have any doubt, then I can discuss. So have you understood this point?
Yes, sir.
You have understood, I think. Okay. So let me ask you some question so that I can understand that you are listening carefully. Shaheen Akhtar is there. If you're there, you unmute yourself. Shaheen Akhtar. Shaheen Akhtar. When I will call your name, you just get ready. Otherwise, I will take as absent. That means Shaheen Akhtar is not there. Now, okay. Abhishek Majumdar.
Yes, sir.
Can you tell me what is the other name of this depletion layer? You are not there from the beginning.
Sir, yes, sir. It's a space change region. Space charge region, sorry.
You are not listening carefully. Okay.
Sir,
Kaushik Maji.
so it's a space charge.
Space charge region. Correct. Kaushik Maji.
Yes, sir.
What is the other name
Yes,
of
sir.
this N minus region in this power diode? N minus layer আরেকটা নাম কি? শুভশ্রী ভট্টাচার্য.
Yes, sir.
Can you tell me that question that I asked?
The other name of n minus layer.
Yeah.
drift region.
Correct. It's called the deep region. Can you tell me the objective of providing this deep region, because this layer is absent in normal diode?
Yes, sir. This layer is absent in normal diode, but in power diode, N minus layer is provided to absorb the depletion layer created by the P plus and N minus substrate.
Correct. Okay, so you should listen the class very carefully. Uh,
Yes, sir. Sorry.
anyway, but already it has the attendance has gone down to 29 from 35. I don't know why. Okay, so anyway, today I will close the class here. I will take the attendance. You just wait for some time so that I can take the attendance. Another class I'm trying to take in this week itself, because last week we didn't have any class. Okay, so let me uh, take the attendance. But you should, so these are official class I am taking. You should be present in these classes, and the attendance will be considered, because now the evaluation processes are different. Okay, so we can evaluate different way. So I will consider this for myself. I will consider this attendance and your performance during the class, so that you should.
স্যার
হ্যাঁ বলো।
স্যার একটা কোয়েশ্চেন ছিল স্যার, ওটা আরেকবার বলে দেবেন। রিভার্স বায়াস জিনিসটা, ওই জিনিসটা ওই সময় আমার ছিল না, নেটের প্রবলেম হচ্ছিল স্যার।
হ্যাঁ কি হচ্ছিল?
রিভার্স বায়াস,
হ্যাঁ
রিভার্স বায়াস
হ্যাঁ,
প্রথম দিকে বলেছেন না, ফরওয়ার্ড বায়াস রিভার্স বায়াস, ওখানে রিভার্স বায়াসটা স্যার আরেকবার বলেন।
আমি বলেছিলাম যেটা, যে পয়েন্টটা মেন, বাকি তো সবই বইয়ে পাবে। যেটা আমি মেন বলেছিলাম সেটা হচ্ছে রিভার্স বায়াস বলতে আমরা যেটা বুঝি সেটা হচ্ছে যে তোমার ডিভাইসটাকে বাইরে থেকে এক্সটার্নাল ভোল্টেজ দেওয়া হলো, তারপর ওটা রিভার্স বায়াস হলো যদি এনটা প্লাসে লাগানো থাকে আর পিটা মাইনাসে লাগানো থাকে, দ্যাট ইজ কল্ড দ্য রিভার্স বায়াস। বাট reverse bias is not that external phenomenon. Reverse bias is an internal phenomenon, or both the reverse and forward bias, because the reverse bias and forward bias is determined mainly by the carrier concentration, minority carrier concentration or distribution along the length of the device. Okay, are you getting? বুঝতে পেরেছো তুমি? তাই চলে গেল। Okay, so I think you have understood. So
Sir, I have one question, sir.
শুনছি, বলো।
Sir, ওই যে ইন্ডাকটেন্স এর ক্ষেত্রে যেটা দেখাচ্ছিলেন স্যার, সেকেন্ড কেস মাইনাস আই হলো স্যার, ডিআই ডিটা লেস দেন 0 কেন হলো, ওই জায়গাটা একটু স্যার অসুবিধা।
এটা DID লেস, এই যে এই স্লোপটা,
সেকেন্ড কেসটা স্যার,
সেকেন্ড প্লেসের এই স্লোপটা
হ্যাঁ
বলছো।
এখানে আইটা তো, হ্যাঁ হ্যাঁ স্যার ওইটা স্যার একবার আর এক্সপ্লেন স্যার। আইটা নেগেটিভ বুঝলাম স্যার, বাট ডিআই ডিটা লেস দেন 0 সেকেন্ড কেসে আইটা নেগেটিভ হলে তো
হুম, এটা তো চেঞ্জ হচ্ছে, নেগেটিভ হচ্ছে,
স্যার ডিআই ডিটি
বুঝতে পারছো না?
আইটা,
টাইমটা তো অলওয়েজ পজিটিভ, ডিটিটা তো অলওয়েজ পজিটিভ,
হ্যাঁ
কারেন্টটা
বুঝতে
নেগেটিভ
স্যার
হচ্ছে,
এখানে,
কারেন্টের চেঞ্জটা তো নেগেটিভ হচ্ছে,
আচ্ছা আচ্ছা,
বুঝতে পারছো না? এই স্লোপটা, এই
ও
স্লোপটা
হ্যাঁ
যদি
হ্যাঁ
নেগেটিভ হয়, এই স্লোপটা
হ্যাঁ
কখনো
হ্যাঁ
পজিটিভ হতে পারে? বুঝতে পেরেছো? টিএফ এর
না
স্লোপ
এটা নেগেটিভ, হ্যাঁ
হয়, তাহলে টি1 এর স্লোপটাও তো
হ্যাঁ
নেগেটিভ।
হ্যাঁ হ্যাঁ স্যার স্যার বুঝতে পারছি বুঝতে পারছি। হুম, আচ্ছা আচ্ছা। আর স্যার এই যে ভোল্টেজের ডাইরেকশন, এটা কি ওই প্রথমে যে এই বাঁ দিকের ছবিটা স্যার রেফারেন্স অনুযায়ী কি ওটা মানে ভোল্টেজের ডাইরেকশনটা চেঞ্জ হচ্ছে, ওটা যেহেতু পজিটিভ এলডিআইডিটি পজিটিভ ছিল
বলো,
বলে ওদিকে এখানে নেগেটিভ হচ্ছে বলে,
বলো কি বলছো?
স্যার ওই যে ভোল্টেজের ডাইরেকশন যেটা দিয়েছিলেন, স্যার ভোল্টেজের ডাইরেকশন যেটা ছিল ওটা স্যার ওই প্রথমে যখন মানে পজিটিভ ছিল এই যে রেফারেন্সে, তখন যে ডাইরেকশন ছিল এখানে ডিআইডিটি নেগেটিভ হচ্ছে বলে কি ওর এলডিআইডিটি ডাইরেকশনটা ভোল্টেজের ডাইরেকশনটা কি চেঞ্জ ওই জন্য চেঞ্জ হচ্ছে?
হুম, ভোল্টেজের ডাইরেকশনটা চেঞ্জ হচ্ছে
আচ্ছা আচ্ছা।
তোমার ডিআইডিটার ওপর। ডিআইডিটা কিরকম হচ্ছে তার উপর ভোল্টেজ
হ্যাঁ
ডিরেকশন চেঞ্জ
আচ্ছা
হচ্ছে। কারেন্টের চেঞ্জটা কোন দিকে হচ্ছে? ইন্ডাকটেন্স অলওয়েজ অপোজ দ্য চেঞ্জ ইন দ্য কারেন্ট। মানে বুঝতে পেরেছো? ইফ দেয়ার ইজ এনি চেঞ্জ ইন দ্য কারেন্ট দেন ইন্ডাকটেন্স অপোজেস দ্যাট। তোমার কোন যেদিকে চেঞ্জ হবে তার উল্টো দিকে ভোল্টেজ ইনডিউস হবে। এটা হচ্ছে ইন্ডাকটেন্সের প্রপার্টি। এবার তুমি দেখো চেঞ্জটা কোন দিকে হচ্ছে তার ঠিক অপোজিটে ভোল্টেজটাকে ইনডিউস করবে। তো এই যে ফার্স্ট দুটো কেসে দেখো চেঞ্জটা একদিকে বলে পোলারিটি একদিকে আছে, মানে দুটোই দেখো ডিআইডিটি টা নেগেটিভ, সেই জন্য এটা একদিকে আছে। তারপর এটা দেখো ডিআইডিটি টা পজিটিভ, সেই জন্য
আচ্ছা।
এটা পোলারিটিটা এরকম দিকে আছে।
আচ্ছা বুঝতে পারছি।
Okay, thank you. If you have any other doubts, you can ask me in the next class. So for now, I am ending.